Good morning, students. Today we are going to discuss about the Maxwell's equation of an electromagnetic wave. It is nothing new. These are the equations which we have already studied in the previous chapters. What Maxwell did it, he just made all the four equations, and based on these Maxwell's four equations, the whole study of electrostatics and magnetism can be described and it can be interrelated. So, before Maxwell did those equations, electricity and magnetism were considered as two different entities, but Maxwell put both of them together. The unification of electrostatics and magnetism is done by Maxwell. Okay, the unification of the theory is done by Maxwell. That is why it is called electromagnetic wave theory. So, Maxwell proved that electricity and magnetism are interrelated. So, these are the four fundamental Maxwell's equations. The first Maxwell equation is Gauss law in electrostatics. That is the first Maxwell's equation. Gauss law of electrostatics. We can write it like this: surface integral vector E dot vector ds is equal to q by epsilon 0. We have studied this in the first chapter, Gauss law in electrostatics. Surface integral of E dot ds is equal to q by epsilon 0. This is considered as the first Maxwell's equation because it concerns with electrostatics. Now, the second Maxwell's equation is Gauss law of magnetism. Gauss law of magnetism, and Gauss law of magnetism states that the surface integral of magnetic field around a closed surface is 0, because we studied in chapter 4 magnetic monopoles do not exist. So, when I take the surface integral of magnetic field over any closed surface, the answer will be 0. So, I will be writing like this: surface integral of B dot ds is equal to 0. Surface integral of magnetic field over any closed surface is 0. So, that is from chapter 4. Now, the third Maxwell's equation is Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. So, we already studied Faraday's law in chapter 6. Whenever there is a change in the magnetic flux, an EMF will be induced. So, a change in the magnetic flux will produce an induced EMF. So, that is Faraday's law. So, I am going to write like this: the line integral of the electric field vector E dot dl. dl stands for line integral, ds stands for surface integral. So, here line integral of electric field can be written as minus d phi subscript b divided by dt, minus d phi by dt. d phi is called the magnetic flux, and this can be rewritten as minus d by dt of minus d by dt of integral b dot ds. So, I will write like this, minus d by dt of integral B dot ds. So, here you can see with this equation I am relating electric field with the magnetic field. I am saying both of them are interrelated. That is what Maxwell did. Okay, that is the third equation. Now, fourth Maxwell's equation is called modified Ampere circuital law. Modified Ampere circuital law. Fourth one. Modified Ampere circuital law. I have just put surface integral B dot ds, just showed that S as the subscript to tell that it is surface integral. Okay. Now, let us see what is modified Ampere circuital law. You already studied what is Ampere circuital law. Line integral of magnetic field around any closed loop is mu 0 times the total current. So, that is when current flows through a conductor. But what happens when current flows through a charging capacitor between the plates of the capacitor? So, between the plates in chapter 2 we have studied between the plates of the capacitor there is only variation in the electric field happening, because inside the capacitor it is dielectric. Dielectric will not conduct because dielectric is an insulator. So, there is polarization happening inside the dielectric, due to which electrical effects are transmitting. That is what we have studied in the capacitor chapter 2. So, taking that into consideration, Maxwell is modifying Ampere circuital law like this: integral B dot dl over any closed surface is equal to mu 0 into I. Usually we studied in integral B dot dl is mu 0 I, but now Maxwell is modifying this as mu 0 into IC plus epsilon 0 d phi E by dt. This is the modified form of the Ampere circuital law, where IC is called the conduction current, which means the current flowing through a wire, and mu epsilon 0 d phi E by dt, rate of change of electric flux. Epsilon 0 d phi E by dt, rate of change of electric flux. So, this is called conduction current. This current is happening inside the capacitor plates, which is called displacement current. So, this entire quantity is called displacement current and IC is called the conduction current. Conduction current is happening through the wire and displacement current is happening inside the capacitor plate. We do not have more to learn about displacement current because that is excluded from our syllabus. You only have to remember the name. So, here when you look equation 4, you can see I am again relating magnetic field with the electric flux. So, from these equations itself it is clear that electric field and the magnetic field are interrelated. Electric flux and magnetic flux are interrelated. In short, I can say electrostatic and magnetism are interrelated, that is electromagnetic wave theory. This is what is proved by the Maxwell. Okay, so these laws are called Maxwell's equations. These equations are called Maxwell's equations. Now, electromagnetic wave exert pressure because electromagnetic waves carries energy and electromagnetic wave travels as energy. So, they can transport energy and momentum. So, they can exert pressure, and this pressure is called radiation pressure. So, I will say once more, when an electromagnetic wave falls on any surface, it can exert pressure on that surface, and that pressure is called radiation pressure. I can write radiation pressure like this. P subscript R, radiation pressure, which can be written as intensity of the wave divided by speed of light. Radiation pressure is given by the equation intensity of the wave divided by speed of light. And for visible light, the radiation pressure is 7 into 10 raised to minus 6 Newton per meter square. 7 into 10 raised to minus 6 Newton per meter square is the radiation pressure for the visible light. So, for different electromagnetic waves like X-rays, gamma rays, etc., the radiation pressure will be different. Okay. So, that is all for now. Thank you.